Hey, what's going on YouTube? What's up? So I think that we're back live, and today's going to be a fun stream. I hope that all of the streams are fun, but this one I'm very excited for. So we are going to play the natural number game. It is an excellent online game that you can play for free just by typing that into your web browser. And I've played through this once many years ago, probably in the middle of the pandemic, like in the first 6 months of the pandemic. I ran through this game, and it's just beautiful. It's just a really, really nice game. What we're going to do is we are going to construct the natural numbers. We're going to construct the natural number system that we all know and love, 1 plus 1 equals 2, and things like that. And we're going to construct a lot of the properties that we expect from natural numbers out of the axioms. In particular, we're going to be working from the Peano axioms, which is one of the first axiomatic systems, I think, of the modern formalist age. I don't really know, something like that. So it's not as low level as ZFC. ZFC is like our current modern mathematical axiom standard system. But you can prove the Peano axioms, and the Peano axioms are a reasonably good place to start. In math, you can choose where is your starting point, and then you define what are the rules of the game. If A and B, then C, and you want to prove propositions like that from simpler truths like A and B, and then you make mathematical arguments called proofs that lead to new truths, and then you take those as a truth and you keep combining and building all of mathematics. A lot of people don't see this very much at all in high school. I think everybody gets some introduction to proofs in geometry, at least in the United States, but they don't do a very good job, in my opinion, of showing the axiomatic, systematic nature of mathematics. So I hope that this stream will give you a little bit more of a sense of what pure math is like. But on the other hand, it's also very new. So we're going to run through the natural number game, which is a tutorial for learning Lean 4. This is a very, very modern way of doing mathematics that is all about encoding these mathematical statements into types and type theory. Types are, I have a deep love, and they're near and dear to my heart because I'm an iOS app developer, and the Swift programming language, I think, was one of the first super mainstream programming languages that featured a type system so, prominently. Really, really elegant, beautiful language. It's too bad that it's still so tied only to iOS development. But the same type of types that Swift is built on, all of modern mathematics. There's a group called the MathLib community, and they are attempting to formalize all of mathematics into type theory. And it's a stronger type system than what programming languages have. I think it has dependent types. I don't know enough about the really technical stuff. We're here learning. I'm here learning alongside you. But I know it's a stronger type system, and it is the leading contender, as I understand it, for pragmatic, actual use cases in research level mathematics. So I'm stoked. I hope you're stoked. This is going to be fun. Let's get started, y'all. I forgot to message my Discord, so add everyone live now. All right, this is going to be fun. So I want some background music, and our options are either classical guitar or lo-fi hip hop. Somehow I feel like lo-fi hip hop is a very fitting vibe for this stream. So let me pull up that. And I tried to get my Glove 80 online, but it seems like it's out of batteries. I haven't been using it in months. So hopefully we can switch to the Glove 80 for some nice mechanical keyboard ASMR as we play this game. Let me switch over to... Yeah, I should have gotten this running. I meant to get this running before the stream, but in any case, let's play a little bit of Stim Clicker until we can get to the lo-fi hip hop. This is a different, very beautiful, equally beautiful game. Beautiful in different ways. So I just want to get to the lo-fi hip hop. Which ones do I want? That one. Yeah, we're getting some clickiness. Do I want Subway Surfers? Yeah, okay, so DVDs are now gonna make sounds once they bounce. Let's get the breaking news thing. 200 stim, and then, alright, so this is not the natural number game. This is just my method to get some audio. Alright, there's the lo-fi hip-hop girl. Let's do this, We're almost there. How much do we need? 250? Okay. There we go. While we're at it, it's not going to take that long. Let's get the Subway Surfers going. All right. Cool. Let's do this, y'all. This is going to be fun. So. I'm going to turn down audio like halfway. All right. Okay. All right. Natural number game. Let's do this. So, welcome to the natural number game, an introduction to mathematical proof. In this game, we will build the basic theory of the natural numbers 0, 1, 2, 3, 4, ... from scratch. Our first goal is to prove that 2 plus 2 equals 4. So, like, literally, we're going to be proving really simple statements like 2 plus 2 equals 4. Why is that true? That's such a simple thing, but it is something that you have to prove. All right, so I've got chat up on the right. Next, we'll prove that x plus y equals y plus x. So we're going to prove commutativity of addition in the natural numbers. And at the end, we'll see if we can prove Fermat's last theorem. What? I don't think we can. We'll do this by solving levels of a computer puzzle game called Lean. That's really funny. I like that line. We'll see if we can prove it. And the answer is probably going to be no. I'm pretty sure that this is research level math, is trying to prove and formalize FLT in Lean. So we're going to be solving levels of a computer puzzle game called Lean. Read this. Learning how to use an interactive theorem prover takes time. Tests show that the people who get the most out of this game are those who read the help text like this one. To start, click on Tutorial World. And now this is a new version. Ooh, we get strong induction world, even odd world, and prime number world. Cool. Okay, so this is a super fun thing from what I remember. All right, so if we do the smaller window, it said click on tutorial world. So I guess we click here. All right, what happens if I keep the font large? Welcome to tutorial world. In this world, we learn the basics of proving theorems. The boss level of this world is the theorem 2 plus 2 equals 4. So I like how they break this down into bosses, and it's very video game. You prove theorems by solving puzzles using tools called tactics. The aim is to prove the theorem by applying tactics in the right order. Let's learn some basic tactics. Click on Start below to begin your quest. Okay. All right, the RFL tactic. If x and q are arbitrary natural numbers, then 37x plus q equals 37x plus q. Okay, so we're trying to get this reflexive property. We're trying to prove that x equals x, that any number equals itself. And I guess for whatever reason, we are just making that a little bit more interesting and complicated by saying that our goal is that if we have two numbers, a scalar multiple of the first plus the second equals itself. All right, so read this first. Each level in this game involves proving a mathematical theorem, parentheses, the goal. The goal will be a statement about numbers. Some numbers in this game have known values. Those numbers have names like 37. Other numbers will be secret. They're called things like x and q. We know x is a number, we just don't know which one. In this first level, we're going to prove the theorem that 37x plus q equals 37x plus q. You can see xq colon n in the objects below. Okay, so down here, xq colon n, neat. Which means that x and q are numbers. We solve goals in Lean using tactics. And the first tactic we're going to learn is called RFL, which proves all theorems of the form x equals x. Okay, so it looks like this is a built-in axiom or a built-in tactic to Lean that any number equals itself, I think. Okay, so right now we have this active goal. We have these two objects. This is like in a mathematical proof. You say, let x and q be natural numbers. So this is in a classical proof. You say that, like, let x and q be elements of n, or be natural numbers if you spell it out completely. Now the goal is 37x plus q equals 37x plus q. And I guess it's telling us that all we have to do is just type RFL. Execute. Level completed. Okay, so this is easy. This is easy. Let's get some dopamine and stimulation from this. We got this. Does this website have a dark mode? Because I noticed that we are on our own. Oops. Okay, so there's two different modes. One that's more code editor-like and one that's more like a typewriter. I think that I'll probably switch to the code style. Can we force layout of mobile? If we do this, then everything will continue looking decent. What is impressum? Okay, yeah. Legal. Notes. Editor mode. Is there no dark mode? I would love to help them build dark mode. Okay, alright, we're just gonna have to use a browser extension for this. Alright. If x and q are arbitrary natural numbers, then 37x plus q equals 37x plus q. But this font looks awful. The contrast there is really, really awful. So I think we're going to have to just use a white screen instead. Is it better in typewriter mode? In typewriter mode, it's okay. Yeah, in typewriter mode, the fonts look okay. So we'll use dark mode with typewriter mode. Okay, so level completed. We got a little celebration note here. Great. The RW tactic. If x and y are natural numbers, and y equals x plus 7, then 2y equals 2 times x plus 7. Okay, so this is like a rewriting tactic. In other words, substitution. So we can substitute y equals x plus 7 into this little formula. So like given 2y, then replace y with x plus 7. Okay, in this level, the goal is 2y equals 2 times x plus 7, but to help us, we have an assumption, h, saying that y equals x plus 7. Okay, so we have assumptions listed somewhere, h. Check that you can see h in your list of assumptions. All right, oh, here? Okay, so assumptions. H is defined as, the hypothesis H is y equals x plus 7. Okay. Let me know, folks, how the audio levels are, if the background music is too loud or not. Lean thinks of H as being a secret proof of the assumption, rather like X is a secret number. Okay, yeah, so this is a given. This is like an assumption that we can take as like an axiom, kind of, or a truth that we're starting from. Before we can use reflection, we have to, quote unquote, substitute in for y. We do this in Lean by rewriting the proof H using the RW tactic. Okay, so first execute RW bracket H to replace the y with x plus 7. Okay, so if we have these assumptions, I think that once I execute this, we're going to update these assumptions. Okay, can you take it from here? Click on show more help if you need a hint. Okay, so here the goal transformed. So first, like our assumptions stay the same and our objects stay the same between these two, but now the goal changed. Now we have two, on the left-hand side we had 2 times y, and now we have 2 times x plus 7. Again, that's because we used the rewrite command to substitute y. Cool. Can we get the font bigger? Bigger. Okay. So, that's all right. That's feeling good. I'm going to take off the top at some point, like this huge blue bar, but